So this is a lesson on lens formulas, so how to use basically math to kind of predict where the image from a lens is going to form. So there's a couple of, I'm going to say, idiosyncrasies that exist here, so we're going to have to pay attention to these. So first, let's draw a kind of image from our lens, so we can draw using our two rules for ray diagrams. This is a bad ray diagram, but whatever, you get the idea of what it's supposed to be like. So we have to define a few key terms that exist for our lenses. So the first term that we're going to define is our HO. So this is the height of the object, or the size of the object that exists. Then we have our HI, which is the size of the image. So HO is height of object, HI is height of image. Next thing we have is DO, distance of object, distance really from the object to the optical center of the lens, or the center, the midpoint of the lens. So we're going to say DO is the distance of object from the optical center of the lens, like this distance right here. Similarly, we have DI, which is distance of image from the optical center of the lens. Right? The last thing we have is our, is our focal length, which is the same, it's defined as before, distance from optical center to the focus. Right? So again, we have height of object, height of image, distance of object from lens, distance of image from lens, and the focal length of the lens. Right? So this is what we just talked about. We have different terms, but the equations that are going to be used involve one or more of these terms. So one thin lens equation states that 1 over f equals 1 over do plus 1 over di. This is the thin lens equation. Again, f, focal length, distance of object from lens, distance of image from lens. Magnification equation is m equals hi over ho equals negative di over do. And again, you kind of have to be careful here. The negative can move from here. It could be here technically, right? You can move the you can multiply everything by -1 and kind of move the negative from side to side. And we have to be careful and aware of that basically when doing our calculations. The last equation that we'll be learning is something to calculate the power of the lens. So P for power equals 1 over focal length. The units of power are diopter, or you can just write D. And whenever you get a prescription for your lenses, your power is often written in like it's units of diopter. So you'll have like -2 D, or -1.5, or positive 1.25 D. And this diopter really tells you what your power is. And you calculate that by doing 1 over the focal length in meters. Right? So this is the 3 equations that we will need to know in order to do calculations and stuff. This is the idiosyncratic part that I was talking about. There are certain sign conventions that we must kind of follow when dealing with lenses. Sign conventions are basically, because they're on opposite sides of the lens, because DO is on this side and DI is on this side, one of them I have to assign, okay, DO will be positive when this is true, or DI will be positive when this is true, so that I can differentiate, so I can know when DI is being formed on this side and when DI is being formed on this side, right? So I have to be able to tell, and so I use sign conventions. So again, DO is always positive, so the distance of object is always taken to be positive, and the distance of image is, the distance of object is never negative. So always positive, never negative, right? The distance of image is positive for a real image. Again, distance of image is positive when the image is real. That also is the same thing as saying the image is inverted. And again, here you kind of have to be careful because real images are formed on the opposite side of the lens. So this over here is a real image because it was formed on the other side of the lens. Again, contrast that with mirrors where it was the other way around. Real images were formed on the same side of the lens. Here we need a screen to kind of catch the image that's going on the other side of the lens. And so conversely, DI is negative when you have a virtual image, or an upright image, or an image on the same side of the lens. These three things mean the same thing, right? So it's negative when you have a virtual, it's positive when you have real. This is for DI. HI and HO are, again, that was the only confusing part, I would say. HI and HO are fairly simple. Anything that's above the principal axis will be positive. Anything that's below the principal axis will be negative. So this is so you can kind of tell for a real image, assuming DO and HO are positive, for a real image, your DI will be positive, but your HI will be negative because it will be inverted. And that's where the negative from this equation shows up, right? Because you have to flip the sign there, because DI is positive when HI is negative, because real images are inverted, right? So inverted. Again, because technically if you start with a object that's below the principal axis, the inverted would be above the principal axis. So it kind of depends, but usually we'll only be doing objects where you're above the principal axis. Upside down objects are not really done as often. The last kind of thing that you have to remember is that a converging lens has a positive focal length because its F lies on the real side or the other side of the lens. A concave lens, the focal point lies on the same side of the lens. The other side is F prime, and this makes this focal length negative. So the focal length is negative for a diverging lens and positive for a converging lens. All right, so using these sign conventions, basically we have to be able to solve problems like this. So this is what we're going to be practicing. I don't know whether to make this 8 questions. Interesting. I think I'll do all the questions in a separate video. No, I'll just continue here. So a converging lens has a focal length of 17 centimeters. Focal length equals 17 centimeters. Is this positive? You always have to think to yourself, whenever I write down something, is that positive or negative? Converging lens, focal length is positive. Candle is located 48 centimeters from the lens. Distance of object, 48 centimeters. Positive or negative? It's positive because distance of object is always positive. Where will it be located? Okay. So I have 1 over F is 1 over DI plus 1 over DO. Or DO plus DI, whichever one. I have to find 1 over DI essentially. So I'm going to move this entire term to this side, which makes it 1 over f minus 1 over do. And I'm going to put some values in here, 1 over positive 17 minus 1 over 48. So 1 over 17, again, I can put in my calculator. You can even put this entire thing in if you want. You can put, like, open a bracket, 1 divided by 17, close bracket, minus, open another bracket, 1 divided by 48, close bracket. But 1 over 17, you can do it step by step, kind of, is 0.0588 minus 1 over 48 is 0.02083. So if you do the subtraction here, you get 0.03799 roughly, right? And this is still, however, equal to 1 over di. This is not the final answer, right? And to think of how you can calculate di, you can kind of do it two ways. You can, if you have 0.37, you can kind of move di up here. So 0.03799 di equals 1, and then move this entire term down to the denominator, or this entire number down to the denominator, where you have di equals 1 over 0.03799. Alternatively, you can just take the inverse of both, or reciprocal of both. So I'm going to flip this fraction around and say di over 1. And so I'm going to flip this fraction around and say 1 divided by 0.03799. So I kind of flipped both. So this flipped and this flipped. So if I do 1 divided by 0.03799, I get distance of image is 26.32 centimeters away. This is a positive distance of image. That means it's a real image, right? And that's what type of image will be formed. It's also inverted. We know that because it's a real image, right? So this is how you do the calculations for the lens equations, using lens equations. And the same equations generally apply to mirrors. There's just and pretty much the same sign conventions as well. So you could calculate images of mirrors, but we're going to be just doing the lenses part. Diverging lens has a focal length of 29 centimeters. Focal length equals 29 centimeters. Diverging lens, very important, negative focal length. Virtual image of a marble is located 13 centimeters from lens. Distance of image is given to us as 13 centimeters. Virtual image, di is negative, right? So I have to find where is the marble located, or I have to find 1 over do, question mark. So I know 1 over f is 1 over do plus 1 over di. I'm going to find do, so I'm going to move this and to the other side, where I'm going to subtract it. One over f minus 1 over di equals 1 over do. And so here, 1 over f would be 1 over negative 29 minus 1 over negative 13 is 1 over do. And then I can kind of put that in my calculator. 1 divided by negative 29 is negative 0.0344. Subtract 1 divided by negative 13 is negative 0.076923. So 1 over do is equal to um, 0.04244. Right, so that's what I'm getting when I do this calculation. And that's 1 over do. So again, can kind of like flip or take the reciprocal of both sides. So DO over 1 equals 1 divided by 0.04244. Just kind of turn this numerator becomes denominator, this numerator becomes denominator. I'm kind of like just flipping the fraction. And so if I do the 1 divided by 0.04244, I get DO equals 23.56 centimeters, and it's positive. And it should be positive because if it's negative, I made a miscalculation somewhere. That means because DO I can never get DO as a negative number. If maybe I should rephrase that. When you do the lens equation and then you get DO as negative, you've done a mistake somewhere. If you do the magnification equation, like this equation, and you get DO somehow as negative, you're just going to flip that negative to a positive. Okay, so I think we're just gonna I don't know, do we want to power through this? It's going to be a long video, but oh well, might as well. I'll just explain the homework now as well so that it's easier for you, I think, hopefully. So a toy of height 8.4 centimeters, height of image is 8.4 centimeters. Converging lens, so it's positive focal length, in case we need to know that. An inverted real image of height 23 image. Inverted image, so height of, this is height of object, is 8.4. Height of image is negative 23 centimeters. What is the magnification? Here we have to be careful because magnification is always a positive. So this is the case where we're kind of, because it's an inverted image, we kind of have to move the negative. The formula was originally HI over HO, and there was a negative with the DI over DO. But we're going to bring that negative over here. Alternatively, if you don't want to remember to bring the negative, that's fine. HI is just negative 23. HO is 8.4. 23 divided by 8.4 should be negative 2.738, but we're just going to make magnification a positive number, positive 2.738. Now it's key to note that I can use any half of the formula I want. So magnification equals HI over HO. This is one formula on its own. Magnification equals negative DI over DO. This is another formula on its own. HI over HO equals negative DI over DO. This is another formula on its own. I can use any part that I need, basically. So this is a very division, basically, and I change the negative to a positive. And magnification is basically saying, okay, this image got 2.738 times bigger because it was 8.4, now it's 23. Small toy building block is placed 7.2 centimeters in front of a lens. Distance of object 7.2 centimeters, always positive. An upright virtual image of magnification 3.2 is noticed. Where is the image located? Interesting. Yes. DI is what I have to find. Magnification is what I'm given, 3.2. So again, I'm going to use this formula. Magnification is negative DI divided by DO. So I'm going to put some numbers in. 3.2 equals negative DI divided by 7.2. So again, I'm going to take this up to the top. So negative DI equals 3.2 times 7.2, which is equal to 3.2 times 7.2 is 23.04 is negative DI. So I'm just going to move the negative to this side, multiply both sides by -1. I don't know how you want to think about that, but the negative can just shift over from one side to the other, right? So DI is negative 23.4 centimeters, and the negative sign here makes sense because it's a virtual image, so DI should be negative. So this is correct. A coin of height 2.4 centimeters. So height of object is 2.4 centimeters. Upright virtual image, height of image is 1.7 centimeters. Positive again because it's upright and virtual. What is magnification? HI over HO, 1.7 over 2.4. 1.7 over 2.4 is 0.7083. And now the magnification is less than 1 because your image is getting smaller. All right, so that was hopefully easy-ish question. This is again very similar. Focal length is 23 centimeters. Distance of object is 32 centimeters. Calculate where image of frog will be located. Distance of image is question mark 1 over f equals 1 over do plus 1 over di. You're finding di, so move this to the other side. 1 over f minus 1 over do equals 1 over di. So I can put some numbers in. 1 over 23 minus 1 over 32 equals 1 over di. Again, 23 is positive because it's a converging lens. Do is positive because it's always positive. So again, I'm going to put 1 divided by 23 minus 1 divided by 32 right in my calculator, and I can get 0.01222 equals 1 over di. And to find di, I take the inverse. I just flip this, so it's 1 over 0.01222, which is 81.7 centimeters. And should this be positive? Yes, it is a real image that is formed, and therefore positive distance of image. Right, so that was correct as well. Calculate focal length. So this is kind of a different type of question, but it's very diverging lens. So 1 over, okay, what am I given? Located, so distance of object is 53 centimeters. Image of pencil is formed 18 centimeters, so 18 centimeters, but it's upright and virtual. So it's negative 18 centimeters. This is the key here. And then I just, use my formula. 1 over f is 1 over do plus 1 over di. 1 over f equals 1 over 53 plus 1 over negative 18. So I can just, 1 over, which is basically 1 over 53 minus 1 over 18, right? That's what I'm doing. But I can just put 1 over 53 plus 1 divided by negative 18 right in my calculator, and I get 1 over f is negative 0.036687. Very okay. Hopefully we see the pattern now. The last step is always taking the flip of this thing. So f equals 1 divided by this number, right? And if I do 1 divided by that, I get focal length is negative 27.25 centimeters. The negative makes sense because it's a diverging length, so I want my answer to be negative. And that, again, you'll see that it shows up in your answer. You don't have to make it negative 99% of the time, right? So it's just a kind of confirmation that you're doing something right. Okay, the last two questions are super easy. So for lens has a focal point of 0.5 meters. So power of the lens is 1 divided by focal length, which is 1 over 0.5, which is 2 diopter. It is a convex lens or a converging lens, and I know that because my power is positive, or my focal length was given to be positive. Right, that's very easy. Focal point of negative 0.4 meters. Again, power equals 1 over the focal length, it's 1 over negative 0.4, which is, I think, negative 2.5 diopter. it is a diverging lens because I have a negative focal length. So this concave lens. And that concludes basically all the questions that we could solve. I don't know whether to make one more Snell's Law video depending on how people are feeling. Maybe I'll put one up later, but this is the main video that we did on Friday that you kind of have to learn about new calculations. So yeah, there you go. See everybody in class.